The next chapter spotlights statistical process control, SPC, though we won't actually do any statistics. In this chapter, we will first discuss different forms of process variation, contrasting natural and assignable variation, and we'll also differentiate control charts from process capability. We'll then understand those control charts, including X-bar charts and R charts, and we'll learn how to interpret these charts to determine if a process is in control. We'll then learn process capability with CPK and relate that to Six Sigma. They're really the same calculation. And then finally, we'll cover additional metrics, including those that you'll see later in your CSSC manual as you prep for the certification exams. So let's start with the difference between natural and assignable variation, then how control charts and process capability help us to evaluate the quality of a process. Recall our definition of quality: consistently meeting customer value expectations. Consistently means the same or regularly. And the opposite of consistency is inconsistency or variation. We've emphasized how variation is a killer of quality. We like stable, in control processes that produce consistent outputs. And I know stability sounds boring to some, but it's critical to quality. Recall that people consume roughly 2 billion Coca-Cola products every day. And each of those experiences involves a moment of true judgment about product and service quality. Each experience needs to be consistent, or people may avoid Coke products in the future. And even a 1% dip in that demand means 20 million fewer Coke products consumed every day. But all processes vary. No matter how many times we execute a process, it will not always take the exact same amount of time, at least down to the second, and it will not always turn out exactly the same. That difference may or may not be problematic. In this chapter, we examine process variation statistically, but don't let the term statistics worry you. The math is not particularly difficult, and you're only responsible for interpreting the results, not calculating them. Again, all processes have variation, and we can attribute variation to two causes, one being natural variation and the other being assignable variation. First, natural variation, also called chance, random, or common variation, relates to small, negligible, underlying variation in any process. It's random and cannot be controlled, so it's always present and cannot be eliminated. So natural variation does not generally present issues in meeting customer expectations. Processes with only natural variation can be considered stable, which means in control. And so no action is likely needed to improve the process. For instance, you can set your alarm clock for the same time each morning and follow the same process to get ready for work, yet you'll rarely leave at the exact same time every day. A few minutes early or late is generally not a problem. Natural variation typically does not disrupt a process. In contrast, assignable variation, also called non-random variation, is just that. It's not random. It can be assigned to a specific cause. That is, there's a reason for the variation, and we can fix that reason. Assignable variation tends to be larger and more significant than natural variation, and assignable variation reflects a process that is not in control. It's not stable. However, if we eliminate the source of the assignable variation, we can reduce that variation and potentially get the process back in control. So assignable variation is the target of SPC. For instance, suppose that you're often late getting out the door in the morning. So you apply the 5 whys. Why are you late? You tend to oversleep your alarm. Why do you oversleep? You go to bed too late. Why do you go to bed too late? Well, you're staying up late watching TV and so forth. The whys can go on and on until you get to that root cause. The point is that if you can identify and correct that underlying source of the variation, that root cause, the variation goes away and your process will become more stable. It will be more consistent, which is good. So statistical process control, SPC, targets assignable non-random variation. In fact, SPC tools are used to identify assignable variation, ideally before the process goes out of control, meaning before it produces defects. In other words, SPC alerts us to potential issues before they become bigger problems. We can then launch Lean or Six Sigma to fix the underlying causes and ensure better value delivery to our customers. So we'll define statistical process control, SPC, as the statistical evaluation of process variation. And again, variation is the opposite of consistency. We look for signs of assignable variation that lead us to identify and then fix assignable causes. And we can take corrective action before the defects occur. Again, corrective action before the defects occur. Let's relate two tools of SPC, control charts and process capability. First, control charts help us determine if a process is stable. Is the process in control? Control charts help us distinguish between natural and assignable causes of variation. And we'll learn how to calculate limits on what is natural and what is not natural variation with the help of the upper control limit, the UCL, and the lower control limit, the LCL. Again, control charts distinguish natural and assignable variation in processes to determine if the process is stable. Is it in control or not? And if it's not in control, we can hit it with DMAIC and or Lean to fix the underlying causes and bring it under control. And notice here that we are not yet considering what the customer wants, meaning customer expectations. We're just looking at process stability. Our second tool, process capability, then looks at the customer expectations, specifically their allowable variation. Process capability, which is abbreviated CPK, determines if the process is capable of consistently producing within customer specifications. Can the process consistently deliver what the customer wants? And we'll learn how to assess the process variation relative to customer specifications, customer specs, with the upper spec limit, the USL, and the lower spec limit, the LSL. And we saw this exact idea in the Six Sigma chapter with our coffee example. Remember that we wanted our coffee temperature to be between 130 degrees, the LSL, lower spec limit, and 160 degrees, the USL, the upper spec limit. Again, process capability, CPK, determines if the process can consistently produce within customer specs. If not, we can hit it with DMAIC and or Lean to get that process back to be capable. So control charts assess the control, the stability of a process, and process capability assesses the ability of the process to meet customer specs, their expectations. Following our get ready for work example, suppose that we're returning to the office after working at home for a few months. So, ugh. Well, we first have to establish our get ready for work process. We'll first determine if our process for getting ready is stable. That is it relatively consistent with respect to timing? That's process control, and we can use control charts to assess this. We then have to figure out if our get ready for work process will then get us to the office consistently on time, not too early and not too late. So here we can apply process capability, CPK, to evaluate this. Again, SPC targets assignable variation, helping us see assignable non-random causes. And ideally, we can take corrective action before actual defects occur. SPC helps us find issues before they become significant. Summarizing, control charts evaluate process control, stability, and then process capability evaluates if the process will consistently meet customer specifications. So control charts are essentially a requirement to test for process capability. That is, you first need a stable and in control process before you then assess that process against customer specs. So control charts, then process capability. The next section will cover control charts, and then the section after that will cover process capability.